Okay, so last week we talked about the first Fourier transform and how efficient calculation of discrete Fourier transform using divide conquer methods, radix 2 algorithm. So this week let's start with another topic which is called digital filter. So as you why digital filter? Because we want to implement the filter in digital domain. So input signal of the filter is digital and output signal is also digital, and the implementation of the filter is also digital. So as you aware about that, there is a called active filter, passive filter, all are here designed using analog domain. I think if you have completed your analog electronics course, where you have already designed that active low pass filter, active high pass filter using op-amp circuits. So those are analog filters. So input signal is analog signal, it's passed through that this circuit and then produce an output signal which is also an analog. Here we talk about the digital filter. As you know that why digital filter, why not analog filter? As you know that why the digital signal person, the advantage is that it is nothing but an algorithm. So when I talk about the digital filter, it also is nothing but an algorithm. Instead of you can say the component and then there will be active device, passive device. Instead of that, here I have an already digital signal and I pass through an algorithm which will act as a digital filter and output will be a digital. Then at the output we can apply that analog to digital to analog conversion and produce the analog signal and feed to that natural system. Let's think about that your equalizer. Suppose you have a sound system, you want to design an equalizer whose job is that to emphasize certain frequency and maybe attenuate certain frequency components. So which is nothing but a filter. So or you can say the hearing aids that emphasize in particular frequency band. So we require a filter, but that filter is in digital filter. So signal is digital and filter is nothing but an algorithm and output is also a digital signal. So when you talk about the digital filter, then it is an algorithm. So how do I implement that algorithm? So there may be a different kinds of digital filter. So let's like the normal filter. If I talk about the normal filter, so what is there? According to the magnitude characteristics of the transfer function, as you know that the function, the classification of the filters are different kinds of filter. Maybe the low pass filter, there is a low pass filter, there is a high pass filter, there is a band pass filter, band stop filter. What is low pass filter? So it will allow this frequency only. Elsewhere the attenuation, the amplitude of the magnitude response is 0. So the signal will exist only those component, and so this is not signal, this is a frequency characteristic. So that's why HLP e to the power j omega. So it is nothing but a frequency magnitude plot, or I can spectrum of the digital filter. So this is the spectrum where that filter is only exist minus omega c to plus omega c. Omega c is cutoff frequency, and you know that digital frequency is pi is normalized digital frequency, which is nothing but because you know that fs is equal to 2 pi. So maximum frequency of possible in the digital signal is pi, maximum oscillation minus pi to pi. So if I define the magnitude response of the filter, it is nothing but a omega c and minus omega c. So this is called low pass filter, because low frequency are only pass and high frequency are stop. Magnitudes are 0. So high frequency is stops, low frequency pass. So that's why it is called low pass filter. Similarly, there is a high pass filter, or let's say band pass filter. So band pass filter, if you see, the particular band of frequency is pass. You know that if I say frequency transform, there is a negative axis and positive axis. In real application, I may only look into this side. This side I may agree, but in theory there will be both side minus omega c plus omega c. Similarly here also there will be a band exist and minus axis, and also because the frequency response is minus pi to pi. So that's why I can say this band of frequency will pass. The frequency response is like this. This is the positive side and this is the negative side of the frequency, and this is the band. So this is called pass band, and rest elsewhere it is 0. So this is band pass filter. Then high pass filter. What is high pass filter? What is the maximum frequency in the digital signal? Is the pi. Pi to minus pi. So if I say high pass filter means let's say 2 kilohertz high pass filter. That means the after 2 kilohertz signal will exist, below 2 kilohertz signal should not exist. So that's why the below 2 kilohertz, below omega c signal is 0, and after that it is exist up to pi, because maximum oscillation is possible minus pi to pi. So that is high pass filter. Then I say band stop filter. Particular band will be stopped. That means particular band frequency. So this to this band, these bands of frequency signal should not be exist. So it is combination of, I can say, low pass filter and a high pass filter. It is nothing but a band pass filter. So basically, if I able to design, if you see that if I able to design this low pass filter, I can implement band pass filter, I can implement high pass filter, I can implement band stop filter. So ultimately boil down to how do I implement, how do I design this low pass filter? What should be the algorithm to design this low pass filter? That is our target. Okay. So that different kinds of filter and their frequency response I got. Now ideally it is possible that ideally I want a low pass filter. Let's say I am not drawing that negative side. Let's say talk about only the positive frequency 0 to pi only. Let's only think about the one band, not two band, one band 0 to pi, let's say positive frequency. So ideally in low pass filter, if my cutoff frequency is omega p, it should be sharp transition. So there is after omega p, then and there it should be 0. But ideally it is not possible to implement an ideal filter which is just after omega p, all frequency will be 0. So instead of ideal, when we want to implement in algorithm, it will becomes and some sort of this kind of this black line, this kind of frequency characteristics. So what is the meaning of this? Meaning is that, so I can say this is my omega p. Omega p supposed to be 1. Let's say omega p supposed to be 1 in here. Okay, supposed to be 1. But this the dotted line is the ideal filter, that one I want, but I have implemented the solid black line filter. That means there is some variation in here, and there will be instead of sharp transition, there will be a gradual transition, and there will be some variation in here also. So this part is called pass band. Pass band. So this part is called pass band. This part, the frequency component, the power will be exist. Elsewhere it is supposed to be 0. But so this is pass band and this is stop band. This portion is stop band. But if you see, even if the pass band, there is some variation of the signal, which is called del p. Del p is the variation, plus minus variation. If I saw that there is a middle line in here, I can say there is a variation in plus del p and minus del p. So this del p is called pass band ripple. Del p is called pass band ripple. There will be a ripple, that means variation in instead of straight line, there will be a variation. That variation is called ripple. So since this ripple exists in the pass band, that's why it is called pass band ripple. Similarly, in the stop band also there will be a variation. So that is called, instead of 0, there will be some value. So which is nothing but a del s. So this del s is called peak stop band ripple. So del p is the peak pass band ripple, del s is the peak stop band ripple, because this band is stop band. After omega p we call stop band. Let's say the stop band is defined in here, instead of omega p directly, and real filter this transition is gradual. So this part omega p, omega s minus omega p is called transition band. Transition bandwidth. So this is my transition bandwidth. So in any filter where I want to design, there will be a pass band ripple, there will be a stop band ripple, there will be a transition bandwidth. And omega p, omega s, or the omega p is normalized stop band frequency and omega is normalized edge frequency of the stop band, normalized edge of stop band frequency. So what is del p? How do I define? What kind of practical specification will be given to me to design the filter? So what is there? If I say the pass band is my pass band, omega p is my pass band frequency. So the pass band is 0 to omega p is my pass band. So within 0 to omega p, what I want, the amplitude should be 1, unity. But there will be a deviation with del p, which is called peak ripple in the pass band. So instead of 1, so instead of this, I will get an variation. So that variation, this peak to peak variation, if it is del p, then I call this is pass band ripple. So I can say instead of 1, my filter magnitude, filter frequency magnitude is 1 minus del p and 1 plus del p. This is 1, this 1 minus del p this side and 1 plus del p this side, peak to peak del p will be here. So my magnitude response of the filter including ripple is not 1. It should be 1 minus del p or it may be 1 plus del p. I not exactly get 1. So del p is called pass band ripple. As you say, when you design and let's say, well, I think most of the electronics engineers will be there. So as you know, there is a ripple in DC converter, DC power supply. What is the ripple? I want a constant source, DC source, 5 volt DC. But since I am derived that 5 volt DC from a AC source, there will be some ripple. So ripple is nothing but a top up at 5 volt, but plus minus some variation will be there. That is called ripple. So here also I want 1, but there will be a plus minus variation. That is called pass band ripple. Similarly, what I want, my stop band, if omega p is my pass band, then highest frequency is my pi, maximum frequency possible is pi. So my pass band varies from omega s to omega 2 pi, because after that signal is not there. So in that region, what I want 0. I want it should be 0. So if this is my pass band and this is my stop band in here, omega s, and this is my omega p. So this portion, omega s minus omega p, is called transition bandwidth. And this omega s is my stop band edge frequency. So in the stop band, what I want 0. But instead of 0, there will be some variation. But this variation is not both sides, because minimum is 0. So I can get a sine kind of variation which is minima is 0. So if the peak is del s, so I can say it is varies from 0 to del s. So instead of 0, it will be del s. So maximum value is del s and minimum value will be 0. So this del s is called stop band ripple. Have you understand? So when we design a filter, instead of ideal filter, in ideal filter stop band ripple is 0, pass band ripple is 0. So I want 1, then transition bandwidth is 0 and then all are 0. But this is not possible. So instead of that, what I will get a pass band ripple, stop band ripple and transition bandwidth. So how this specification will be given when you want to design a filter? So in practical specification, the loss function will be defined in dB. So if I say what is the value of my maximum amplitude of my passband H mod of H omega, this has to be expressed in dB. So it is in voltage. So if it is square, then it will be power. So if it is voltage, then I know it is 20 log 10 mod of H is omega is the magnitude response of the filter. Now what is passband ripple? Passband ripple is alpha p in dB, alpha p in dB. So del p in dB. So it is nothing but a minus 20 log 10 1 minus del p in dB. Minimum stop band attenuation alpha s will be given in dB, which is minus 20 log 10 del s will be given in dB. So when you talk about in practical specification of a filter, this will be look like this. That design a low pass filter with passband edge frequency Fp is equal to 2 kilohertz and stop band edge frequency Fs is equal to 2.5 kilohertz. Then what is the transition bandwidth? The transition bandwidth delta is equal to omega s minus omega p. In hertz, I can say it is nothing but a Fs minus Fp, which is nothing but a 2.5 minus 2 kilohertz. So it is nothing but a 0.5 kilohertz, which is nothing but a 500 hertz. So my transition bandwidth is 500 hertz. So instead of stop band edge frequency, they may say I require a passband frequency or cutoff frequency Fp is equal to 2 kilohertz and transition bandwidth is 500 hertz. So either they can define transition bandwidth or they can define stop band. So this is the practical problem is given, and where passband ripple is equal to 0.01 dB and stop band is equal to my 60 dB and sampling frequency is 16 kilohertz. I have to design the filter. So what I have to require? I have to find out the del P. How do I find out the del P? I know del P is minus 20 log 10 1 minus del P is equal to 0.01. So from there I can calculate del P. Similarly, I can calculate del S. 60 minus 20 log 10 del S, then del S is equal to this one. So I know del P and del S. I know transition bandwidth. But when we design a digital filter, I have to express in normalized frequency, normalized discrete frequency. That in my first lecture, if you remember, I said in case of digital domain, the omega is radian per sample. It is not radian per second. So if I want to find out omega p, what is the value of omega p then? So omega p is nothing but a 2 pi Fp by Fs. This Fs is not this Fs, sampling frequency, capital Fs. So I can say omega p is equal to 2 pi into 2 kilohertz in this case divided by Fs is 16 kilohertz. So 2 kilohertz, 16 kilohertz. So kilohertz cancel. I can say 2 pi into 2 divided by 16. So is equal to pi by 4. Then what is omega s? Omega s is equal to, again it is nothing but a 2 pi into 2.5 kilohertz divided by 16 kilohertz. So kilohertz is not required. So I can say it is nothing but a 5 pi by 16. What is the transition bandwidth in delta transition bandwidth? It is 500 hertz. I can directly say that omega s minus omega p, which is nothing but a 5 pi by 16 minus pi by 4. Or I can say, let's say instead of given Fs, they have given that transition bandwidth 500 hertz. Again I can say 2 pi 500 hertz divided by 16 kilohertz. So I can say it is nothing but a pi by 16. So this difference and this one will be matched. This one also will be pi by 16. So when a practical things will be given, so if I told you, suppose let's say take a slide. Suppose somebody told you design and digital low pass filter whose cutoff frequency FP is given 3 kilohertz and transition bandwidth delta is equal to 200 hertz, okay, and stop pass band ripple is 0.01 let's say dB and stop band ripple is 60 dB. So pass band ripple from dB I can calculate del P and del S. That is straightforward. But I have to, so when I want to draw this filter specification, low pass filter, so ideally it should be look like this, 3 kilohertz and the rest will be 0. This is ideal. But instead of ideal scenario, what I will get? I will get some variation, then here and also some variation. So I can say this is nothing but a del P. So del P I can calculate. This is nothing but a del S. I can calculate. This is my transition bandwidth. Sorry, this is my transition bandwidth. So transition bandwidth I can calculate delta. So delta, once I say it is omega, then I have to normalize the frequency. So what is my omega P? Omega P is nothing but a 3 kilohertz divided by sampling frequency. Let the sampling frequency is 8 kilohertz. Then I can say 8 kilohertz. 2 pi into 3 kilohertz divided by 8 kilohertz. So it is nothing but a 2 pi into 3 divided by 8 is equal to 3 pi by 4. Then what is omega S? Omega S is equal to, so what is omega, so Fp is given, what is Fs? Fs is equal to stop band frequency, edge frequency, it is nothing but a 3 kilohertz plus 3 kilohertz plus transition bandwidth 200 hertz, so which is nothing but a 3.2 kilohertz. So omega S nothing but a 2 pi into 3.2 kilohertz divided by 8 kilohertz. So I can say 3.2 pi divided by 4. Now I get the filter specification. So I know omega Fp, I know everything. Now I have to design that low pass filter. So how do we interpret the filter specification? That is very important. Let's I give you an example. Suppose I told you design and band pass filter whose lower cutoff frequency is let's say 1 kilohertz, upper cutoff frequency is let's say 3 kilohertz. So pass band width is 2 kilohertz and the transition bandwidth is 200 hertz and the pass band ripple and stop band ripple is given in dB. So hertz to omega conversion, it is nothing but a normalized discrete frequency, radian per second. Normally hertz, that when I say the discrete domain, why it is maximum frequency is pi? Because pi radian per sample, it is not radian per second. That's why we write in small omega. When I say analog frequency, we write in this omega. This is radian per second and this is radian per sample. That's why we divided by Fs, F by Fs. Okay. So I think this portion you have understand. So what is there? I have to design and digital filter. So what is a digital filter is nothing but an algorithm. So what will be given to me? They will give you provide a specification of the filter which will be described in terms of frequency, ripple and transition bandwidth. Now from there I have to derive the filter parameter. I have to derive omega p, omega s, pass band ripple, stop band ripple and then I have to go for the design of filter. So before designing of the filter, I have to draw the frequency response of the filter and the frequency response of the filter is only provided by the specification. Is it clear? So you have all are clear that pass band ripple, stop band ripple and all those things. Now I come to the how do I implement this filter? So if I say digital filter, it is nothing but a system. So digital system whose sampling, whose unit impulse is Hn, and my signal is nothing but a, let's say, x of n passes through Hn, I get Yn. So I can say, if I in Z domain, the Hn is nothing but a Hz. So Hz is the transfer function of the filter, and which is meeting the specification. So frequency response is given of this Hz. So transfer function frequency response is given. So whatever the people will give you, the design this kind of filter, so from there I have to derive Hz. So Hz must meet the specification given by the user. Okay? And it has to be causal system. If it is non-causal, then how do I practically use it? Now there is two kind of filter. One is called IIR filter, another is called FIR filter. What is IIR? Infinite impulse response filter. What do you mean by infinite impulse? If you see, if Hn is the impulse response of the filter, then Hn has an infinite, very infinite, this impulse response is infinite. It varies from minus infinity to infinity, n varies from minus infinity to infinity. If it is causal, it is varies from 0 to infinity. So it is infinite impulse are there. So if I implement infinite impulse response, so if I am able to implement Hn which consists of infinite impulse response, then it is called IIR filter, infinite impulse response filter. Now if it Hn instead of infinite, let's that infinity, I said no, I do not consider the infinite response. Let's I consider only 300 point of this impulse response. So Hn 0 to infinity, but I am considering only 300 point, then it is called FIR filter, finite impulse response filter. So there are two kinds of filter, IIR filter where it is infinite impulse response, FIR filter where it is finite impulse response. So when I say IIR filter, then I can say that Hn in Z domain is nothing but a Hz. So Hz is a transfer function which is nothing but a ratio of a two polynomial. Ratio of a two polynomial. So I can say, as I know that from the Z in the Z transform view, that upper side solution of the upper side polynomial give me the 0, and solution of the lower side polynomial give me the pole. So that's why Hz is called pole 0 filter. So if I am able to implement the transfer function directly in digital methods, then I am implementing IIR filter. But what is the condition? Hz must be stable. So in Z domain, I have to derive the transfer function from the given specification of the frequency response, and that transfer function must be stable in Z domain. And as much as possible, the number order of this polynomial, as much as possible I have to keep low, because if the order of the polynomial is increases, then the complexity of implementing Hz is increases. So if I give you, let's say I give you the Hz transfer function. So if I ask you that I have already discussed about the structure 1 and structure 2 implementation, let's say I give you a filter transfer function in polynomial form Hz. Let's say Hz is equal to 1 plus 2 into z to the power minus 1 plus 3 into z to the power minus 2 divided by, let's say, 2 plus 5 z to the power minus 1 plus 2 z to the power minus 2. Let's say this is my Hz. So what is the order of the upper polynomial? Second order. What is the order of the lower polynomial? Second order. So in this transform there is a 2 pole and 2 0. Now if I told you, can you implement this HZ, digitally implement HZ using structure 2 method or structure 1 method? Let us say structure 1 method you implement. So how do I implement it? Structure 1 realization of this transfer function HZ. So what is there? I know this is nothing but a HZ and there will be a XZ and I get YZ. So XZ I know. So YZ is equal to HZ multiplied by XZ. So if I say that, so HZ I know 1 plus 2 into z to the power minus 1, 3 z to the power minus 2 divided by 2 plus 5 z to the power minus 1 plus 2 z to the power minus 2 into xz. Now if I simplify it, yz into this one 2 plus 5 z to the power minus 1 plus 2 z to the power minus 2 is equal to 1 plus 2 z to the power minus 1 plus 3 z to the power minus 2 into xz. Now if I do this, what is there? Yz 2 into yz plus 5 into yz z to the power minus 1 plus 2 into yz z to the power minus 2 is equal to xz plus 2 into xz z to the power minus 1 plus 3 into xz z to the power minus 2. Now if I see what is the impulse response, I know it is nothing but a 2 into yn plus, so z to the power minus 1, signal is delayed by one sample yn minus 1 plus 2 into yn minus 2 is equal to x of n, so 2 into x of n, so it will 2, this will be 2, so this is x of n, this is not 2, x of n plus 2 into x of n minus 1 plus 3 into x of n minus 2. Now I can say, can I implement this one in a block diagram? Structure 1, I know this is my x of n and this is my y of n. So x of n is delayed by z to the power minus 1, then again z to the power minus 1. So this one is x of n minus 2. So this will be multiplied by 3 and x of n minus 1 will multiply by 2 and both will be added together. Okay, and then it will be added with x of n. Okay, and then it will be fed to y of n. Then y of n is again has to be multiplied by 2. Okay, y of n is to be multiplied, so y of n, then z to the power minus 1, z to the power minus 2, let us say not to put it 2 in here, put 2 in here. So y of n plus this side z to the power minus 1, this will be multiplied by 5 added to here and this will be multiplied by what? 2 and added to here. So this is the structure 1 implementation of this transfer function. So if I able to derive the transfer function from the given specification, then I can implement IIR filter using structure 1 or structure 2 realization, possible. But condition is Hz must be stable in Z domain. So stability means all poles should be inside the unit circle. So that all that condition I have to catch. So there is a procedure to derive transfer function from the given specification that we will discuss during design of IIR filter. Now I said if I truncate that frequency response, instead of infinite impulse, let us say I n number of impulse. So there is an, I can say H0, H1, H2 dot 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 up to H infinite, instead of infinite, I only consider n minus 1. So n number of impulse response I have taken. So it is finite impulse response filter. So H0 will multiply z to the power minus 0, H1 will multiply z to the power minus 1. So I can say H of n into z to the power minus 1. So that is my Hz. So here it is not polynomial. I have not taken infinite impulse response. I have truncated that impulse response. I have taken certain number which is n, and this n is called degree or order of the filter. Now if you see, if I increase the n, then if you see, number of multiplication also increases. Z is a complex number, so number of complex multiplication is increases. So I have to put n as much as lowest possible. But when I put lowest, then it will affect in my characteristics, filter characteristics. So what will be the effect on filter characteristics? That means if I take infinite impulse, then suppose it is an ideal filter. Now once I reduce the order of the filter, it will increase the transition bandwidth. So there is a relationship between the transition bandwidth and order of the filter. If you decrease the order of the filter, your transition bandwidth will be. So if I require a very sharp cutoff, then my order of the filter must be increased. If I require a shallow cutoff, wide, okay, no problem, then order of the filter will be very low. Another condition is there called phase, linear phase. So there is a concept of phase in filter. So Hn is nothing but a system. So the requirement is that it must be linear phase. So what is the concept of linear phase and how it is possible to implement in FIR filter, we will discuss in the next class. Okay? Thank you.